Hey everybody, welcome back. In this video, we're skipping section 4.3 in our book, and we're skipping to section 4.4, which is all about counting. Now, when I say counting, we're going to be learning 5 different ways of counting in different statistical situations. It's definitely, we've got a lot more formulas than we have before, so a calculator can be very helpful in these problems. But I'm going to show you how to do the math. There's a certain amount you can do without a calculator, but at some point you're probably going to want to use a calculator anyway. And some calculators actually have buttons that will do such things as permutations and combinations. Okay? So in this section, we are going to be using more formulas than usual, 5 different methods for counting. Now, not all counting problems can be solved using the 5 methods that we're going to learn, but they do provide a strong foundation for the most common real applications. Okay, so we're going to start with the first method of counting. If you recall, in section 4.2, we talked about the multiplication rule. And this multiplication counting rule is the first method that we're learning for counting. And it's basically the same as the multiplication rule that we learned in section 4.2, in that if you have a sequence of events, here it's assumed that the events are independent events. It doesn't say that in the book, but if the first event can occur n1 ways, the second event can occur n2 ways, the third event can occur n3 ways, and so on, the total number of outcomes is found by just multiplying the number of ways each event can occur. So in other words, it's going to be n1 times n2 times n3, etc. But we kind of should already know this from section 4.2, because it's when they're a sequence of events and they're independent events, since one doesn't depend on the other, we know that we're supposed to multiply the probabilities when we use the word and. And a sequence of events is essentially a bunch of events using the word and, even if they don't specifically use the word and. Okay, so let's see an example of this. So this is an example from our book. A computer hacker finds that a password is entered in as 1, 2, 3, 4, 5 digits. Okay, we can see those 5 little dots here are the 5 digits. So that the characters are hidden. So we know there's 5 characters, and it turns out that there are 92 different characters with a typical keyboard. At least in this problem, they're saying there are 92 different characters that could be used in their password. And then they're asking us, how many different passwords are possible using 5 characters? Okay, so let's answer their first question. Their second question is, what is the probability of guessing the correct password on the first attempt? So this is an example of the multiplication counting rule that I was just talking about. So because there are 92 different characters for each digit, if we want to count the total number of possible passwords, we just need to take, 92 choices, and then because there are 5 digits, we just need to do 92 times 92 times 92, a total of 5 times. So 1, 2, 3, 4, 5. And obviously, we already want to use a calculator. Most people would not want to calculate this by hand. And it's also the same as 92 to the 5th power. If you prefer to write it as an exponent. So let me grab my calculator real quick. So you can either type in 92 times 92 times 92 times 92 times 92, or you can just type in 92 to the 5th power on your calculator. And that gives me a very large number. Okay, so that gives me a lot of digits. Okay, so the number I have here, I'm just going to read the digits, is 659,081,5232. Okay. Now what we've counted there is the number of possible passwords. That's a heck of a lot of passwords. Okay. So let me switch to the other view. Okay. So as you can see here, we're just multiplying the number of possibilities for each digit, and that gives us the number that I just read to you. It's actually 6,590,815,232 possibilities. Now, to answer their other question, we can see that if we wanted to guess the correct password, there's only one correct password. So the probability of guessing a correct password is going to be one correct password, so that's only one outcome in our event, over the 6,590,815,232 possible passwords. So if we're just guessing a password at random and assuming that the 5-digit password was made at random, this would be our probability. And if you type this into your calculator, it will give you a decimal, which has a lot of zeros and then 152. Notice they've rounded this to 3 significant figures. So for the first non-zero digit, once you reach the first non-zero digit, you're going to have a total of 3 digits. However, as they point out in the book, unfortunately, there are sophisticated programs that allow hackers to try large numbers of likely possibilities, beginning with the commonly used but highly ineffective password of password. So I know a lot of people will do things. Here, password wouldn't make sense because they only have 5 digits. But people do things like password or password 123, or they'll choose the name of one of their pets. So if hackers get a hold of some other information, they might be able to guess someone's password just based on if they find out the name of their pet. Like if their name, the name of their pet is Max, then their 5-digit password might be Max 27. And if the person is 27-year-old person, that would be pretty easy to guess. Okay? But just guessing at random, your chances of guessing a 5-digit password is extremely low. Okay, so that is called the multiplication counting rule. And so when we count the number of possibilities, that is rather large. Okay. All right. So the next rule that we're going to learn about, remember we're learning a total of 5 different ways of counting today, is the factorial rule. Okay, so the factorial rule says that the number of different arrangements where order matters of n different items when all n of them are selected is n factorial. So I know it looks like it says n, right, with an exclamation mark. At least that's what it looks like it says to me. But that exclamation mark is actually read as factorial. Okay, so it's read as n factorial. And all it means is you start with n, and then you count down until you get to 1, and you multiply all the numbers. Okay, so quick example of a factorial. If we just pick a number like 5, what would 5 factorial mean? Well, we would write 5 with an exclamation mark, read 5 factorial, and all it means is that you start at 5, and you count down and multiply all of the integers until you get to 1. So it's going to be 5 times 4 times 3 times 2 times 1. Now, I don't require you to get a specific calculator, but a lot of scientific or graphing calculators do have a way of doing factorials for you. So there's two ways you can do it. You can either figure out on your calculator if your calculator has an exclamation mark, or it might say FACT for factorial. Then you could just do that. You could just type in 5 factorial. Alternately, you can write it out the way I did, and then on any calculator, you can just type in 5 times 4 times 3 times 2 times 1. But obviously, if you have something like 20 factorial, that would take a long time to type in, because you'd have to do 20 times 19 times 18 times 17, all the way down to 1. Fortunately, most of the problems don't involve 20 factorial. Anyway, 5 times 4 times 3 times 2 times 1 should give you 120. So 5 factorial is equal to 120. Okay, and based on your individual calculator, if you're looking for the factorial button, it may even be a button on the calculator itself, or for example, in the case of my calculator that I'm using, a TI-30XS Multiview, I would have to press PRB. That stands for probability. And then when I press PRB on my particular calculator, I can see that the third choice is actually an exclamation mark. So I would just go down to that, and then that would give me the factorial. Okay. So calculators can really help a lot, but I will show you how to do all of these problems on any calculator. As long as your calculator has the ability to multiply and divide, it's still possible to do all these with formulas, even if your calculator doesn't have a factorial button. Okay, so let's continue on to the next slide. So a little bit more information about the factorial rule. The factorial symbol, exclamation mark, denotes the product of decreasing positive whole numbers. Remember that positive whole numbers are the same as positive integers, so counting numbers. And as we saw, like 5 factorial, we just counted down until we got to 1, and then we multiplied all of them. And then the only thing that you need to realize that you might not have known is 0 factorial is actually 1. You may or may not need that on your homework, but it's good to know just in case you need to know it. And it's not on the slides, but it also turns out that 1 factorial is also equal to 1. Okay, so those are a couple of special cases. So 0 factorial is 1, and then 1 factorial is also 1. And of course, 2 factorial would be 2 times 1, which is just 2. Okay, so the nice thing about the factorial rule is it's based on the principle that the first item may be selected n different ways, the second item may be selected n-1 ways, and so on. This rule is really the multiplication counting rule, modified for the elimination of one item on each selection. So for example, when we just calculated 5 factorial, if I got 5 different markers, each one's a different color, the way it works is we said it was 5 times 4 times 3 times 2 times 1. Well, think of it this way. If I have 5 markers, how many choices do I have for the first marker? Well, I have 5 choices. But then once I choose the first marker, and it's assigned to position number 1, or first place, how many choices do I have for the second marker? Well, I only have 4 left because I've already assigned this marker to the first position. Okay, and then after I've picked my second marker, for my third marker, I only have 3 left. So it's 5 markers times 4 markers times 3 markers times 2 markers times 1 marker. So hopefully that makes sense to you. So it is the multiplication counting rule, but we're decreasing the number of choices after we choose each marker, or well, that doesn't have to be markers, it can be anything. Okay. But what's important here is order does have to matter, and we're counting the number of ways we can order that many objects. That's the factorial rule. Okay, so let's see an example of the factorial rule. So this is an example on arranging letters. Okay, so some words consist of letters which can be rearranged to form other words. When they say other words, they're not talking about words that are necessarily words that are in the dictionary. They just mean arbitrary arrangements of letters. So in this example, we're going to consider the word steam. Before we even read what they're asking us about this word, I want you to notice that with this word, all of these letters are different. So we have S, T, E, A, M. There's a total of 5 letters, but none of the letters are the same. So as long as all the letters are different, we're really just talking about the same thing as having 5 different markers. It's the same idea. Okay, so now that we've realized that, maybe we can answer their first question. So for part A, they ask us, how many different ways can the letters of steam be arranged? So they're not talking about words in the dictionary, they're just talking about how many ways can we arrange all these letters. Now, this is just like arranging the 5 markers. And when they say arrange, they mean in order, okay? So if you think about this, it's exactly the same thing. So for the first letter, because all the letters are different, we have 5 choices for the first letter. But then for the second letter, we've already used one of these letters. So for the second letter, we only have 4 choices. And then for the third letter, we have 3 choices, and then 2 choices, and then 1 choice. So it should make sense to you that the number of different ways you can arrange the letters of steam is the same as the number of different ways you can arrange in order 5 markers. It doesn't have to be letters or markers, it could be anything. So that's just going to be 5 factorial. Okay, which we already calculated was 120. Okay? And then that's good to know. It just happens to be the one that we just calculated. All right, and then as they point out in the book, it's the same process that I was talking about with the markers. Note that this solution could have been done by applying the multiplication counting rule. The first letter could be any of the 5 letters, so there were 5 choices for the first letter. Well, for the second letter, that means we've already chosen the first letter, so there's only 4 choices for the second letter, and then 3, and then 2, and then 1. And then when you multiply the number of possibilities for each letter, that's the multiplication counting rule, you get the same number, 120. So there are 120 different ways to arrange the letters, or to arrange 5 objects in order. All right, so their second question is, if the letters of steam are arranged randomly, what is the probability that the letters will be in alphabetic order? So think about this for a second. It's okay if you want to pause the video. And then think about, well, how many words are there in alphabetic order? If we arrange these letters in alphabetic order, how many possibilities is that? And the answer is just one. Okay, so in alphabetic order for any word, there's only one way to arrange it in alphabetic order. Okay, so A would be first. Whoops, that's not the marker I wanted to use. That one's hard to see. Let me pick a marker that we can actually see on here. So yeah, in alphabetic order, we've got A has to be first, and then E would have to be next, and then after that would be M, and then S, and then T. Well, that's only one arrangement. So the probability that the letters will be in alphabetic order, well, there's only one arrangement that's in alphabetical order, so it would be one favorable outcome. So it's one outcome where the letters are in alphabetic order, and then we said there were a total of 120 possible arrangements of the letters. Okay, so it's going to be 1 out of 120. And notice what we really did here was just like with the last problem, if there's only one outcome, you end up doing 1 divided by the number of outcomes that you counted. And most of your homework problems are that way. It's going to be, when they ask you for the probability, they're usually considering just one outcome in your numerator divided by the total number of possible outcomes that you counted. So that's not too bad, hopefully. All right, so let's continue onward. Okay. All right, so we're going to learn about the third method of counting. So far, we've learned about the multiplication counting rule and the factorial rule. So the next rule, this is the third method that we're learning for counting, is called permutations. And because permutations are kind of similar to something else that we're learning, we're going to kind of talk about both of them at the same time. So we're going to talk about permutations and combinations. That way we can distinguish between the two. Okay, so let's start with permutations. Permutations of items are arrangements in which different sequences of the same items are counted separately. In other words, what they're saying here is that order matters. Okay, so this is similar to the factorial rule that we just did. It's just with permutations, instead of maybe counting how many ways you can put 5 markers in order, you might only, for example, if you had 5 markers, you might only choose 3 of them and count the number of ways you could arrange 3 of those 5 markers, but order still has to matter. Okay, so that's the rough idea. And here in the book they say the letter arrangements of ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. But that's just the same as the factorial rule, because if we have 3 letters, then we would have 3 factorial total possibilities, which would be 3 times 2 times 1, which would be 6 times 1, which is 6. Okay? Cool. Okay, so that's permutations. Combinations is the same idea as permutations, but these are arrangements of objects where different sequences of the same items are counted as being the same. So what's different about combinations is just that the order can't matter. Okay, so with permutations, order has to matter. So think of it as like, you know, first place, second place, third place, where order matters. Whereas with combinations, you'll be selecting objects, but the order can't matter. So instead of having first place, second place, third place, you might just, it's like thinking of if you have 5 markers and you choose 3 of them, well, all you care about is which 3 markers you have, but there's no ordering to those markers that you've chosen. Okay, so that's the rough idea. So they have some mnemonics. A mnemonic is a method of learning based on the letters that words start with. You may or may not find this helpful, but I'm going to talk about it anyway. The way people remember permutations is permutations position. They both start with the same letter P. And position indicates, well, if you're talking about position mattering, like first place, second place, third place, permutations is saying that order matters, so the position matters. Okay, so the alliteration, which means that they start with the same letter P, reminds us that with permutations, the positions of the items makes a difference. In other words, order matters with permutations. And then if you remember combinations committee, those both start with the same letter C. And what that's supposed to tell you is, if you think about it, if you select a committee, for example, a committee of 3 people, and you had 5 people total to choose that committee from, there's not any ordering to the 3 people in the committee. Okay, so order doesn't matter with combinations. Anyway, you may or may not find this helpful, but I thought I would mention it just in case it is helpful. If you're trying to memorize these 2 situations. But to summarize all this, permutations means that order matters, combinations means that order doesn't matter. And you know, if you think of a combination plate at a restaurant, for example, if there are 6 possibilities to put on your combination plate and you're choosing 3 dishes on your combination plate, nobody cares the order of those 3 dishes. There's no order. They're just put on the same plate, right? So for that order of a combination plate, there's no order. All that matters is which 3 dishes you have on your plate, okay? But with permutations, that's where you're thinking more like first place, second place, third place, where the order does matter, okay? So let's start with permutations. Now this is a little bit harder than the first 2 rules that we've learned. So this is the formula for permutations. Now if you have a calculator that will do permutations, technically you don't have to use this formula. But I like to show this formula because I know everyone has a different calculator. And I also like people to just understand what the math means and where it came from. Okay, so with permutations, when n different items are available and only r of them are selected without replacement. Okay, when they say without replacement, they're saying that the number of different permutations where order counts is given by, people read this as NPR. And another way of saying it is n objects permuted r at a time. So the permutations of n objects taken r at a time. Well, our numerator is n factorial, which we already know how to calculate. And then our denominator is parentheses n minus r parentheses factorial. Okay, and if you find this intimidating, we're going to break it down in an example. Okay, but that's the permutations rule. That's where order counts. Okay, so let's see an example of permutations. So in a horse race, a trifecta bet is won by correctly selecting the horses that finish first and second and third. Obviously, when we're talking about a race, first place and second place and third place, the order does matter, right? There's a difference between first place and second place and third place. So we're not just talking about 3 horses in first, second, and third, and just we don't care which is which. So the order does matter here. So you must select them in the correct order. So we're going to be using permutations. The 144th running of the Kentucky Derby had a field of 20 horses. 144th we do not need. The 20 horses we do need. Okay, so let's see what they ask us. How many different trifecta bets are possible? So they're asking us in part A to count the number of possible bets, trifecta bets. And we already said that order matters, so we know that it's going to be the permutations rule. Okay, now looking at this formula, like I said, your calculator may have a button that either says NPR, or like, for example, in the calculator I'm using, I can press PRB, which stands for probability, and then I see that one of the choices in the menu is NPR. NPR is usually how they write it. So the way you would type it into the calculator would be, well, since we have a total of 20 horses, and we're selecting 3 of them to be in first, second, and third place where order matters, this would be the same as 20P3. Okay. So you can either do this using the formula, this formula here, or if your calculator has that button and you want to figure out how to do that, it will calculate it for you, which could be nice if you don't want to have to use this formula with the factorials. Either way is fine, but I'm going to show you how to use the formula just in case. So 20P3 is going to be, well, N is 20, R is 3. So plug it into the formula. In the numerator, we're going to have 20 factorial. And then in the denominator, we're going to have 20 minus 3 factorial. Okay, so we're going to have 20 factorial over 20 minus 3 parentheses factorial. And pretty much everyone should be able to do 20 minus 3 in their head. It's 17. So really we have 20 factorial over 17 factorial. Okay. And then if you're typing this in your calculator and your calculator has the factorial button, you could literally just type in 20, the exclamation mark, divide by 17, exclamation mark, and press enter. Or if not, the other way people used to do these before they had calculators that would necessarily have a factorial button is you can start at 20 and you can count down until you get to 17 factorial and then cross out the 17 factorials. So that's a way of simplifying this formula to make it easier to type into any calculator. So what I'm saying is 20 factorial is the same as 20 times 19 times 18 times 17 factorial. Okay, so 20 factorial is 20 times 19, times 18 times 17 factorial, all over 17 factorial. So notice that I counted down from 20 until I reach the same factorial I have on the bottom. And then we can just cross out the 17 factorials because we have one on the top and the bottom. So then really, we could just type in 20 times 19 times 18 on our calculator, and that'll give us 6,840. Okay. Or alternately, you could use the factorial button, or even better, if your calculator has an NPR button to do permutations, you could just type in 20, and then you would do NPR, and then you would press 3, and then you would press enter, and you wouldn't have to do this whole process. But regardless of how you get the permutation, you should have gotten 6,840. 6840. Okay, and then if we go back to the slides, we can see that they got the same answer we did. This was permutations because order mattered. All right. And then if we look at part B, what's the other question they ask us? If a bettor randomly selects 3 of those horses for a trifecta bet, what is the probability of winning by selecting Justify, that's the name of one of their horses, Good Magic, and Audible to finish in first, second, and third place? Well, if you think about that, just like in the other problems, there's only one outcome where the horse named Justify was first place, the horse named Good Magic was in second place, and the horse named Audible was in third place. So that's really only one outcome in our event over, we said there were 6,840 possibilities. Okay. So that means the probability of having a winning trifecta bet when you have 20 horses, and we're talking about the trifecta bet, so first place, second place, and third place would be 1 out of 6,840. So 1 divided by 6,840. All right. And then here they point out something, which is even though we calculated this probability, it might not be 100% accurate because in the real world, not all of them have the same chance of winning, right? Because some horses tend to be faster than others. You know, like some horses might have a track record of being faster than other horses. So this probability that we calculated here is assuming that each horse is equally likely to be in first, second, or third place. So that's a little bit of a detail there that you might want to think about. But for your homework, we're just going to do 1 divided by the number of possibilities. Okay. All right, so that's permutations. Order matters. Now, I did want to talk about combinations next. Now, on the slides in our book, they actually cover combinations as the 5th method of counting. But because we just talked about permutations, I'm going to jump ahead to combinations because it just makes more sense to me, even though our book covers it as the 5th rule, not the 4th rule. Okay, anyway, I'm jumping to combinations now. So when n different items are available, but only r of them are selected without replacement, the number of different combinations where order does not matter is found as follows. So NCR, C stands for combinations, equals, well, this formula is the same as the permutations formula, so it's n factorial over n minus r parentheses factorial, but it also has an additional r factorial on the bottom. And when they divide by that extra r factorial, that's taking away that's basically, it's sort of like uncounting the possibilities where order does matter. So that r factorial basically just makes it so order doesn't matter. Okay? And then once again, if you want to do these on a calculator, your calculator may have an NCR button, or mine, I do PRB, and then I select NCR. But if your calculator doesn't have that button, then you're going to have to use this formula. Okay, that's for combinations. Okay, so I wanted to do an example of the combinations rule. This is a lottery example. So at least at the time the book was written, in Florida's Cash 5 lottery game, winning the jackpot required that you select 5 different numbers from the numbers 1 to 35, and the same 5 numbers must be drawn in the lottery. the winning numbers can be drawn in any order, so order does not make a difference. So just remember, whenever they say order doesn't matter, or if you're reading the problem and you think about it, if you're just selecting a committee, or in this case, a group of numbers where they're not in any particular order, all we care about is the numbers themselves, not an ordering of the numbers. That's going to be combinations. Okay, so their first question is, how many different lottery tickets are possible? Well, we can see that we have 35 possibilities, and then we're drawing 5 of them. So because order doesn't matter, we know it's going to be combinations. And then n here is always the bigger number. So n is the bigger number, r is the smaller number. Here we can see that n would be the larger number, which would be 35. That's the number of possible numbers. So here we're going to be doing 35C, and then because they're selecting 5 numbers where the order doesn't matter, r is going to be 5. Okay, so it's going to be 35C5. I'm going to show you how to use this formula, just in case your calculator doesn't have an NCR button. So what we're going to do is we're going to plug in 35 for n. So using this formula, we're going to have 35 factorial on the top. Okay, I should have not written so high. Let me write a little bit lower so it doesn't obscure the slides. So we've got 35 factorial on the top, and then on the bottom, n minus r factorial is going to be 35 minus 5, which we can probably do in our head, so that's going to be 30 factorial, times r factorial, so that's going to be 5 factorial. Okay, so we have 35 factorial over 30 factorial times 5 factorial. Okay, and then if you're able to press the factorial button on your calculator, you might be able to type all this in. Otherwise, we can do the same thing we did with permutations. So we can start at 35, and then we can count down from 35 until we get to this bigger factorial on the bottom, which is 30 factorial. And then we can cross out the 30 factorials. So that's how people used to do it before they had calculators that actually had the NCR button. Okay, so let's see that process. So we've got 35 times 34 times 33 times 32 times 31 times 30 factorial, all over 30 factorial. Notice that I stopped at the bigger factorial on the bottom, which is 30 factorial. So then I'm able to cross out those 30 factorials. And then the other thing we had in the denominator was the 5 factorial. But we could just write that out. So that's 5 times 4 times 3 times 2 times 1. Okay, so we have 5 times 4 times 3 times 2 times 1 in the denominator. All right, and then on any calculator, you should be able to multiply. So we could, if your calculator has a parentheses button, we could put parentheses around the numerator and parentheses around the denominator, and then type it in all at once. Or alternately, we can do 35 times 34 times 33 times 32 times 31 on our calculator. For the numerator, so that would give us, for this numerator, we would have quite a large number. So I got, I'll just read the digits to you. So 3, 8, 9, 5, 5, 8, 4, 0. Okay. over the denominator, which is 5 times 4 times 3 times 2 times 1. And that's actually 5 factorial, which you already calculated earlier, was 120. Okay. So then if we do this division, we could do that on any calculator. And that will bring us to 35 choose 5 is how some people would say this. 35 C5 or 35 choose 5. Okay, so let's go back to the slides. And here they did the same thing we just did, and they got 324,632 after they divided. Okay. So granted, it might be easier to just figure out where the NCR button is because it's on most calculators, but it's nice to know how to use the formula just so that we kind of understand where the math came from, even if our calculator does have an NCR button, which most do. Okay, so here we could see that on that particular Florida lottery that they're talking about, there were 324,632 possible combinations. So then let's go back to their other question. So their other question was find the probability of winning the jackpot when one ticket is purchased. Okay, so the thing is, if you buy one ticket, you only get to choose 5 numbers, so one set of 5 numbers. So once again, just like the other problems, it's going to be 1 divided by the number of possibilities. So it's going to be 1 divided by 324,632. That's our probability of winning the jackpot if we just buy one ticket, so we only select one 5-number combination. If we type that into our calculator, we're going to see that that's quite a small probability. So 1 divided by 324,632 is actually 0.0000308. And as they point out in the book, typical lotteries rely on the fact that people rarely know the value of this probability and have no realistic sense for how small that probability is. And my understanding is that some of the other lotteries actually have even lower chances. Like the Mega Millions, your chances are even a lot lower than that. Okay, cool. So that is combinations. And then the last method of counting that you're going to need for your homework in my course is actually the one that they cover 4th in the book. And that's a special type of permutations. Okay, so the permutations rule when some items are identical to others. This does show up in at least 2 of your homework problems. So the number of different permutations where order matters, remember, whenever it's permutations, order matters. However, this is a special case. When n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows. So the formula is n factorial over n1 factorial times n2 factorial ... times nk factorial. So this formula could look a little intimidating, but what it means is n1 would be alike, n2 would be alike, nk would be alike. So each of these factorials on the bottom would just be if some of the items are identical that we're arranging, then because they're identical, we have to divide by the ordering of those identical items. So that's what those factorials are on the bottom. So we're going to see 2 examples of this. The first example is on the slides, and then the other one I wanted to just come up with on the spot because I wanted to do another example like a one of your homework problems. Okay, so let's do the example on the slides first. Example, permutations rule with some identical items. This is survey design. When designing surveys, pollsters often repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Okay, so let's answer their first question. So looking at this formula, we can see that we have n is going to be 10. That's going to be the same as the total number of questions. So we're going to have 10 factorial on the top. And then they said that 2 of the questions are identical to each other. So that means we're going to have a 2 factorial on the bottom. And then 3 other questions are also identical to each other. So that's going to be another 3 factorial on the bottom. So basically all this formula is saying is n would be the total number of questions, and then you have to just divide by a factorial for any of the questions that are alike or that are the same. So because 2 questions were alike, we had to divide by a 2 factorial, and then 3 other questions were alike, we had to divide by a 3 factorial. Okay? And then just simplifying this, we can type this into any calculator, but it's not really helpful to count down from 10 down to 3 factorial really, but we can anyway. It's just it'll take us a while. So we've got 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. And then 2 factorial is 2 times 1. And then we have a 3 factorial on the bottom, so the 3 factorials cancel out. Okay. And then, of course, with all of this, it would be easier to just press the exclamation mark or the factorial button if your calculator has it, but if not, we can still type all this in. So we can do 10 times 9 times 8 times 7 times 6 times 5 times 4 times, well, that's where we stop at 4. And then that gives us the numerator. And then we need to divide by, well, 2 times 1 is just 2. So we're really just dividing by 2 here. So after you do all that, you should get 302,400. 302,400. Okay, what we just counted were the number of possible arrangements. Order does matter, but 2 of the questions were identical, and then another 3 of the questions were identical. So we counted the number of possible arrangements in order of those questions. And as you can see on the slides, they got the same answer we did. Okay, and then let's look at their second question. Their second question is it practical to survey enough subjects so that every different possible arrangement is used? I would say no, unless we have a really big budget, because most studies have no more than about 1,000 people in them. So here, to have all of the possible arrangements, we would actually need 302,400 different surveys. And for typical surveys, the number of respondents is somewhere around 1,000. So that would be a heck of a lot more than the typical survey. Okay, and then I just wanted to do one more example of the permutations rule with some identical items. This example is not on the slides. I'm just going to make this up on the spot. So let's do an example on the number of ways we can arrange the letters in a word where some of the letters are the same. So for the sake of expediency, which means getting this done relatively quickly. I'm just going to choose a word that I happen to see on my computer screen. So how many ways can we arrange? Well, I shouldn't say we. I should say how many ways can the letters in the word seen be arranged? That'd be a more formal way of saying it. So how many ways can the letters in the word seen, and by seen I mean SCENE, be arranged? And obviously when they say arranged, they mean in order, because when you're arranging letters for a word, the order does matter, right? The first letter, the second letter, the third letter, and so on. Okay, so to answer this question, we're going to be using the rule that we were just talking about. So permutations of letters in the word. But what's different about this word, unlike the word steam that we did earlier in this lecture, the word seen has two letters that are identical. So we can see that we have two letters that are identical, these two E's. Two letters are the same. Okay? So if all the letters were different and we had 5 letters, then we would have a total of 5 factorial ways of arranging all the different letters. But here, because 2 of the letters are the same, we have to divide by a 2 factorial to take into account that those 2 letters are the same. All right, so that's going to be, in our numerator, we're going to have 5 factorial because there are 5 letters, but then in our denominator, we have to divide by 2 factorial because those 2 letters are the same. And then you could do the same process with more complicated words, like the word that's popping into my head that would be a lot more complicated would be Mississippi. I don't want to do that on this video because this video is already getting long enough. But like with the word Mississippi, you have a total of what? 1, 2, 3, 4 I's. So for the 4 I's, you'd be dividing by 4 factorial on the bottom. And then, some of the other letters are identical. So for each set of letters that are identical, you count how many are identical, and that will show up as a factorial in your denominator. Okay? But for this quick example, 5 factorial over 2 factorial, well, we already calculated 5 factorial, which is 120. And then 2 factorial is 2 times 1, which is 2. So this would be 120 divided by 2, which is 60. Okay? All right. And then there are a couple of problems in your homework with more letters, longer words with more letters. But just remember, you want to look at each letter, and then any letters that repeat, you count how many repetitions of that letter there are, and that will show up as a factorial in your denominator. And then the total number of letters in your word is the same as the factorial in the numerator. Okay? So, hopefully that's helpful. Thank you for watching. As always, I will see you in our next video.